A wing is a type of fin with a surface that produces aerodynamic forces facilitating movement through air and other gases, or water and other liquids. As such, wings have an airfoil shape, a streamlined cross-sectional shape producing lift. The word wing, from the Old Norse vaengr, for many centuries referred mainly to the foremost limbs of birds, but in recent centuries the word's meaning has extended to include lift-producing appendages of insects, bats, pterosaurs, boomerangs, some sailboats and aircraft, or the inverted airfoil on a race car that generates a downward force to increase traction. Various species of penguins and other flighted or flightless water birds such as auks, cormorants, guillemots, shearwaters, eider and scoter ducks and diving petrels are avid swimmers, and use their wings to propel through water. A wing's aerodynamic quality is expressed as its lift-to-drag ratio. The lift a wing generates at a given speed and angle of attack can be 1 to 2 orders of magnitude greater than the total drag on the wing. A high lift-to-drag ratio requires a significantly smaller thrust to propel the wings through the air at sufficient lift. Aerodynamics of wings. The design and analysis of the wings of aircraft is one of the principal applications of the science of aerodynamics, which is a branch of fluid mechanics. The properties of the airflow around any moving object can, in principle, be found by solving the Navier-Stokes equations of fluid dynamics. However, except for simple geometries, these equations are notoriously difficult to solve. Fortunately, simpler explanations can be described. For a wing to produce lift, it must be oriented at a suitable angle of attack relative to the flow of air past the wing. When this occurs, the wing deflects the airflow downwards, turning the air as it passes the wing. Since the wing exerts a force on the air to change its direction, the air must exert a force on the wing, equal in size but opposite in direction. This force manifests itself as differing air pressures at different points on the surface of the wing. A region of lower than normal air pressure is generated over the top surface of the wing, with a higher pressure on the bottom of the wing. These air pressure differences can be either measured directly using instrumentation, or can be calculated from the airspeed distribution using basic physical principles, including Bernoulli's principle, which relates changes in airspeed to changes in air pressure. The lower air pressure on the top of the wing generates a smaller downward force on the top of the wing than the upward force generated by the higher air pressure on the bottom of the wing. Hence, a net upward force acts on the wing. This force is called the lift generated by the wing. The different velocities of the air passing by the wing, the air pressure differences, the change in direction of the airflow, and the lift on the wing are intrinsically one phenomenon. It is, therefore, possible to calculate lift from any of the other three. For example, the lift can be calculated from the pressure differences, or from different velocities of the air above and below the wing, or from the total momentum change of the deflected air. Fluid dynamics offers other approaches to solving these problems, and all produce the same answers if done correctly. Given a particular wing and its velocity through the air, debates over which mathematical approach is the most convenient to use can be mistaken by novices as differences of opinion about the basic principles of flight. For a more detailed coverage, see lift. Devices to change the shape of a wing. Usually, aircraft wings have various devices, such as flaps or slats that the pilot uses to modify the shape and surface area of the wing to change its operating characteristics in flight. In 1948, Francis Rogallo invented the fully limp flexible wing, which ushered in new possibilities for aircraft. Near in time, Dominique Albert invented flexible unsparred ram airfoil thick wings. These two new branches of wings have been since extensively studied and applied in new branches of aircraft, especially altering the personal recreational aviation landscape. A common misconception is that, to generate lift, a wing must have a longer air path across its top side compared with its underside. Wings with this shape are the norm in subsonic flight. but symmetrically shaped wings can generate lift by using a positive angle of attack to deflect air downward. Symmetrical airfoils have higher stalling speeds than cambered airfoils of the same wing area but are used in aerobatic aircraft as they provide practical performance whether the aircraft is upright or inverted. Another example comes from sailboats, where the sail is a thin membrane with no path length difference between one side and the other. For flight speeds near the speed of sound, airfoils with complex asymmetrical shapes are used to minimize the drastic increase in drag associated with airflow near the speed of sound. Such airfoils, called supercritical airfoils, are flat on top and curved on the bottom. Other examples. The science of wings applies in other areas beyond conventional fixed-wing aircraft, including hang gliders, which use wings ranging from fully flexible to rigid, kites, which use a vast variety of wings, flying model airplanes, helicopters, which use a rotating wing with a variable pitch angle to provide directional forces, propellers, whose blades generate lift for propulsion, the NASA Space Shuttle, which uses its wings only to glide during its descent to a runway. These types of aircraft are called spaceplanes. Some racing cars, especially Formula One cars, which use upside-down wings to provide greater traction at high speeds. Sailboats, which use sails as vertical wings with variable fullness and direction to move across water. Structures with the same purpose as wings, but designed for use in liquid media, are generally called fins or hydrofoils, with hydrodynamics as the governing science, rather than aerodynamics. Applications of these arise in crafts such as hydroplanes and submarines. Sailboats and sailing ships use both fins and wings. Design features. Aircraft wings may feature some of the following: a rounded leading-edge cross-section, a sharp trailing-edge cross-section, leading-edge devices such as slats, slots, or extensions, trailing-edge devices such as flaps or flaperons, ailerons to roll the aircraft clockwise or counterclockwise about its long axis, spoilers on the upper surface to disrupt the lift and to provide additional traction to an aircraft that has just landed but is still moving, vortex generators to help prevent flow separation in transonic flow, wing fences to keep flow attached to the wing by stopping boundary layer separation from spreading, winglets to keep wingtip vortices from increasing drag and decreasing lift, dihedral, or a positive wing angle to the horizontal. This gives inherent stability in the roll direction. Anhedral, or a negative wing angle to the horizontal, has a destabilizing effect. Folding wings allow more aircraft storage in the confined space of the hangar deck of an aircraft carrier. Variable sweep wing or swing wings, that allow outstretched wings during low-speed flight and swept-back wings for high-speed flight, such as in the F-111 Aardvark, the F-14 Tomcat, the Panavia Tornado, the MiG-23, the MiG-27, the Tu-160 and the B-1B Lancer warplanes.